Hello everyone, my name is Crystal London. I will be presenting on the topic of multiple regression. This presentation aligns with Chapter 9 of our textbook, which is also our primary reference for this presentation. This presentation will cover an introduction to multiple regression by answering the question, what is multiple regression? We will discuss conditions and assumptions of the statistic. I will provide a brief demonstration for computing multiple regression in SPSS. We will discuss interpretations of the outputs, practical applications and uses. We will conclude with a brief review and I will provide a list of references. By the end of this presentation, you should be able to answer the question, how can multiple regression analysis add value to the school improvement process? Multiple regression is categorized as a complex associational statistic. Our decision for selection begins by questioning the number of variables in an inquiry. In the case of multiple regression, this will always be 3 or more variables. One dependent variable is being examined as the outcome variable. This outcome will be a scale level measurement. We are led to reference table 6.4. This table demonstrates that for a normally distributed or scale-dependent variable, we can utilize multiple regression. Notice that our predictors or independent variables may be normal, dichotomous, or a combination of the two. Although multiple regression is categorized as an associational statistic, it is best defined as a prediction model. This distinction is delineated in our text description of the difference between correlation and regression. While correlation describes the association between two or more normally distributed variables, regression models allow researchers to predict a normal dependent variable from an independent or combination of independent variables. Remember, in the case of multiple regression, the independent variable must be normal or dichotomous. This statistical computation generates regression models. There are two types of regression covered in our text. The first type is bivariate regression. The second type is multiple regression. A researcher utilizing bivariate regression seeks to understand how one independent variable predicts one dependent variable, hence two-variable or bivariate regression. Multiple regression predicts one dependent variable from a synthesis or combination of two or more predictor independent variables. A condition of these predictor variables is that they must be either normally distributed, that is, scale level measurement, or dichotomous. This condition and others are discussed in the next section of this presentation. The authors of our text indicate that there are many assumptions associated with this statistic. They include that the independent and dependent variables have a linear relationship. This assumption may be checked using a scatter plot. Also, errors around the regression line should be normally distributed. Variances of the residuals should be constant. Residuals are the difference between the expected or predicted value on the regression line and the actual observed value. There should be no statistical significance among these residual differences. Another way of saying this is that the variance of residuals should be constant. Multicollinearity is a condition to avoid. It means that two predictor variables are highly correlated and may need to be combined. The concept of parsimony encourages the researcher to use the least amount of predictor variables possible. This next section will examine how to compute a multiple regression statistic using SPSS. During this demonstration, we will also address our question of how multiple regression can add value to the school improvement process. Our target variable for improvement will be student achievement in mathematics. So, I will briefly demonstrate how to compute a multiple regression statistic using IBM SPSS. I have decided to use a dataset that we've gained some familiarity with. So here we have the updated or alternative high school and beyond dataset. In a school context, teachers and school leaders may be interested in understanding what factors predict student achievement. In this example, I am interested in understanding if a combination of parent education, student motivation, and math grades are predictors of math achievement. I will begin by accessing the Analyze function. Then I will select Regression and Linear. I've identified math achievement as my outcome or dependent variable. My predictors or independent variables include parent education, motivation scale, and math grades. You will notice that parent education and motivation scale are both scale variables. You may also remember that parent education is a summated variable. We combined mother's education and father's education. We found in other tests that these two variables were highly correlated. Because of this correlation, there is a violation of the condition of multicollinearity. So for this example, we've decided to use the combined variable. Math grades is a dichotomous variable. Scale variables and dichotomous variables are appropriate for selection of this statistic. Next to method, we ensure that enter is selected. Next, we go to statistics. We want to ensure that estimates is selected underneath regression coefficient. Also, model fits, and we want to request descriptives. We'll press continue and then OK. Here we have the outputs that have been produced for this computation. We will discuss these outputs in the next section. Now, we will interpret the outputs for this computation. Our first output is the descriptives table. This table displays the mean and standard deviation for all variables entered for this computation. Valid N is also displayed with list-wise exclusions. 73 participants have no missing data. The correlations table is next. The first column displays how the three predictor variables correlate with our outcome or dependent variable, math achievement. All predictors represent a typical or medium correlation to the dependent variable, which is what we want. Also notice that each of these three correlations is statistically significant. Next, we look at how the predictors correlate to one another. We want these coefficients to be low, and they are. If you have read through Chapter 9, you may recall that the authors noted that the father's education variable was too highly correlated with mother's education. This presented an issue of multicollinearity and prompted us to combine the two variables into a summated variable, parents' education. One final note is to remember that the values on the opposite side of the ones diagonal are duplicates and should be disregarded. Our third output focuses on variables entered and removed. This table lists all independent variables selected for this computation. Our outcome variable is listed as a footnote. Method indicates that we have requested simultaneous regression or that all variables be considered at the same time. Our model summary follows with a multiple correlation coefficient that considers all predictors simultaneously. Our adjusted R-squared coefficient tells us that the combination of parents' education, math grades, and student motivation accounts for 32.4% of the variance in math achievement. A prediction model used here can predict 32% of the outcome. Values displayed within the ANOVA table indicate that the synthesis of the predictor variables is statistically significant. The coefficients table indicates that when all variables are considered, each of the three predictor variables will contribute significantly to a prediction equation. The coefficients table also helps you to create an equation or formula in which you could predict the dependent variable, in this case, math achievement. So the constant is negative 3.421. Remember this equation? This constant is your y-intercept or b variable. We will change the order here and insert our constant. Next, we will consider the unstandardized coefficients for each predictor variable. We insert our coefficients as the m variable or slope of our equation. 1.112 times parent education plus 3.189 times students' motivation plus 4.668 times math grades. I can now use this model to predict the math achievement Y of a student given information or data on their parents' education, their individual motivation, and their math grades. With these values, I could estimate an expected math achievement score. Now let's return again to our question of how multiple regression can add value to the school improvement process. You are the principal of ABC High School. You and your staff have set the goal of improving math achievement for all students. An analysis of your school's data profile indicates to your team that student motivation, prior math grades, and parents' educational background may affect this end-of-the-year goal. Using the available data from the previous year, you run a multiple regression analysis to produce this prediction model. Using this model and student information, you are now able to estimate or project scores for each student. Interim goals may include initiatives to increase student motivation, maybe through a school-wide incentive program, or examine instructional strategies for prerequisite courses that address lower performing students. Remember, this model only addresses 32% of the variance, so adjustments can only affect 32% of your outcome. This presentation provided a detailed overview of the multiple regression statistic. Although our decision tree identified the statistic as appropriate for complex associational inquiries, the regressional nature of this statistic allows the researcher to predict outcomes on the dependent variable based on a combination of independent variables. We identified conditions and assumptions that need to be met in order to justify a selection of this statistic. A brief demonstration was provided for computing this statistic in SPSS. Using the outputs, we extracted a prediction model and applied it to a local problem of practice. I hope you found this presentation helpful. Here are the references. Enjoy the rest of your week.